Welcome to SolarWorks for Illinois. I'm Tim Montague, your host. Today is March 31st, 2020. Today, solar plus battery storage, the business case for Midwest manufacturing. I'd like to welcome my guest, Marc Thrum, Vice President of Intelligent Generation, to the show. Before we formally introduce Marc, we're going to do just a little bit of housekeeping. As many of you know, we host this event on a monthly basis, and we do record the events and post them on our website. You can find all of that at cesnrg.com/podcast. We have two upcoming events that are scheduled in April. We're going to do a case study of a solar project that we built in the northwest suburbs. Simmons Knife and Saw goes solar with Colin Murphy. It's a pretty cool project, fully attached, 437 kW, 5-degree tilt rooftop array. So if you want to geek out on some of that technology, we will get into that, but also just how the executive team decided to go solar. And then on May 19th, I'm so happy to have Anthony Starr, the director of the IPA, coming on the show. We're going to get an update on the Illinois solar program. So if you're working in Illinois or considering a solar project for your facility in Illinois, this is a great opportunity to have some direct interaction with Anthony Starr, who is the director of the Illinois Power Agency. Today we have Marc Thrum, MBA, Vice President of Intelligent Generation. And Marc is an electrical engineer by training. He is also an adjunct faculty at IIT, the Illinois Institute of Technology, and he spent many years at Whirlpool before that. But Marc has been working in the storage industry now for the past 10 years with a small company based here in Chicago called Intelligent Generation, and I'll let Marc tell us a little bit more about that. But welcome to SolarWorks for Illinois, Marc.
Thank you. Good morning, Tim, and thank you very much for having me on your show.
Intelligent Generation and Continental have been collaborators for quite a few years, so we have a very good working relationship with you guys. But tell us a little bit about how you got interested in storage and how the company got started.
Oh, sure, with pleasure. So by education, I am a mechanical and electrical engineer, and I started my career in sort of big process industries, cement making machinery, paper mills. And after my MBA, I went to a more, I would say, traditional Fortune 500 company that was Whirlpool. And that's what brought me to the United States. As you can hear from my accent, I have to get this out of the way. So I'm German and French, but I've been in the US since 2003. And I was working at Whirlpool in various strategy and product quality jobs. But then in 2010, I met the founder and CEO of Intelligent Generation. His name is Jay Marhofer. And I met him more on a private, personal basis through, he's an attorney, a lawyer, and he was involved in some pro bono work in Michigan, where I live. I met him through some good causes he was supporting here, and we became friends and met on our values before we actually realized that we had some meetings on the minds on some businesses. And when I understood what he wanted to do with some of the patents he had written around, around energy storage, around the future of electrical power on the grid, I thought there was something really interesting here and decided to join him in his adventure. So that was 2010. That's how we started, got into joining him in the startup, and we got incubated at Illinois Institute of Technology. Great. And for me, it was coming back to my roots of electrical engineering, so I was happy to do that too.
Yeah. And this concept of the virtual power plant, was that part of your business model from the get-go?
From the very beginning. And it was even part of the patents that had been filed and that have since been granted, yes.
Yeah. So as most of the professionals in the solar industry know, storage is the holy grail, right? For a variety of reasons. The sun doesn't shine all the time. And so if you can store some of that energy in a battery, you can then utilize it after hours or before hours. But there's also a whole value stack, and that stack is unique to geographic region. Here we are in Northern Illinois, we're in PJM. In Central and Southern Illinois, we're in MISO. And I was at a conference on solar and storage in New York City just a month ago. And even though some of the participants there were in PJM, things are different because the IOUs are different, the utilities are different, and the rules are different. So every region has their unique value proposition and quirks. So today we really want to focus and shine a light on how does storage work for Midwest, especially manufacturers. That seems to be a sweet spot for us here in Northern Illinois. A, we have a lot of manufacturing, and B, solar and storage really pencils well for them. As you and I have learned over the last couple of years, everybody wants storage until they see the price tag, and storage doesn't always pencil, but when it pencils, it's eye-poppingly lucrative, and the ROI is wonderful. So I want to talk a little bit about that, but where would you like to start with this whole value stack of storage in the Midwest?
Well, perhaps with a preface. When you say, storage works in the Midwest, there's two elements to this question. There's the function, and then there's the question of does it pencil? Storage is not new. It's been around for a long time, and the notion of off-grid solar power actually often requires batteries for solar energy at night. These kinds of proposition, the fishing cabin in Canada that is off grid. So there is fundamentally nothing new to the notion of energy parking in the battery in order to have power on demand, right? So it functions, and that functions everywhere. There is an enormous level of technological improvement with stationary energy storage. We go from lead acid batteries, the type you had in the car, to lithium ion powered, the kind that you have in your pocket. And getting here to the second part of the question is, how does it pencil? And here I think, Tim, that you want to direct really the questions, and I will try to target the answers to really our manufacturing audiences, the business leaders who are considering solar and are thinking, why should we add storage to a proposition? Nobody wants storage because they want a battery. Actually, we've met a few because batteries are cool. And when you throw names around like Tesla, there's a lot of brand appeal that goes with it. But by and large, nobody wants battery to have storage. Battery is coming to us as a request for backup when industrial customers have had experiences of outages and they want to protect themselves against it. That's one element. But the other side is really energy storage can help a solar power pencil in places where it would not pencil on its own. So it is a nice complement. If you really take it in its most simplistic form, you have energy and power. And solar power is very good at offsetting energy costs on the bill, which are about 50% of the cost. And power is really provided by the energy storage system. So things like demand charges, capacity charges, these are things that power on demand, which is really what a battery provides. These are the line items that we can attack on a bill, and that's what makes storage really pay back.
And then there's also the tax credit, right? If you pair storage with solar, you can take the ITC, the investment tax credit, which is currently 26%, going down to 22% next year. And that 4% may not seem like a lot, but if you're doing a $10 million project, it's a lot. It's $400,000. So there's a tremendous incentive now to pair storage with your solar array if you can make it pencil. So let's get into some of the guts of this, Mark. How does solar and storage work for a use case? And you mentioned demand charges and capacity charges. Here in the Midwest, we have very low demand charges, and so that's generally not something that we're trying to attack, although maybe you have a different point of view, but capacity charges for sure. And for those of you on the West Coast, demand charges are quite high, and that's where storage is really being utilized predominantly to attack demand charges, but here in the Midwest, it's different.
You're right, Tim. So for those customers who've looked at batteries to go beyond energy parking or off-grid protection, a lot of the conversation in the country is indeed about demand charges. You see that in California, on the West Coast, some of the high demand charge areas on the East Coast. And then the vocabulary that gets thrown around a lot is, can we do peak shaving? Can we reduce demand charges? And one sentence that I like to use a lot in this context is, you can use a battery to chop off a peak. All right, if you really have one peak on one day, something that is very, very acute, then you may actually remove it with a battery. But most of the load profiles, the electrical load profiles in the country are driven by industrial use, air conditioning, something that looks more like a hill, where every day looks like yesterday and probably looks like tomorrow, sometimes not on weekends. And so the idea of flattening a hill with a battery is generally not a good proposition. So you can use a battery to chop off a peak, but not to flatten a hill. And so demand charges are generally in the Midwest not a prime business use case for energy storage. So you want to use it for some other things that are more lucrative, that are capacity and transmission charge reductions, also generating some revenue with frequency regulation, but we probably will get into that a little later. So how do we do this? We do this with, actually, let me perhaps share a few slides if I can to go into the background of this, because it can quickly become, let me go there. All right. Is that working? So I'll answer your question. You can see the slide here?
Yep.
Yeah. So, one thing we didn't say here, I should have said this in the introduction, Intelligent Generation, we're a software as a service company only. Our business is really to help end users take advantage of their behind the meter energy storage assets, in a more broader sense, distributed generation assets, and help them make the best out of it. And we do this along a trifecta here that we call earn, save, protect. So the combination and the optimization of this, which is really where we have our patents, both on an individual site, but also on a virtual power plant, which is the notion you mentioned earlier. This is the way it actually comes together. So we can use these to earn revenues in the wholesale market when the customer doesn't need those assets for themselves in a particular moment, save energy on the bill, and when it is properly hooked up, actually protect critical systems by having the battery provide backup. So it's earn, save, protect. We use our software to predict when these things are needed, when it will actually make most economic sense, and then operate them. We do, here's a way it works at a site level. So typically you would have, you, the end customer, with the facility being a customer of the utility. Here we have the logo of ComEd in that case, consuming power from the grid. You may add, solar to it. You see this on the left, but then how does the storage work? How does it get installed? Well, we work with channel developers, with installers, EPC firms such as Continental Electric, who have a lot of experience in choosing, installing, designing, engineering, procuring these energy storage systems, which are more complicated than just straightforward solar. And then we hook into this and do the remote control of the energy storage in order to maximize the benefits. What are these benefits? Backup, reduce all the power-related costs, earn revenue from grid services when that's available. And as you mentioned, Tim, there's the opportunity to enjoy some investment tax credit on the entire renewable energy property within certain parameters and conditions. And that's a whole topic of its own, but that's really sort of how it works. These are the markets that we serve. So really with a concentration here on the PGM interconnection and the mid-continent ISO, so MISO. These are the largest regulated, or let's say, largest territories that are within transmission organization in the United States. So back to your question here, how do we actually do this? How do we get involved in order to make this happen? We really have developed through our software a suite of instruments, of tools that we use that we call the IG Power Suite. The Power Suite is the umbrella name for the suite of products that we have developed. So we have first on the left-hand side what we call the power plan. So this is how we get involved with you, with Continental Electric, with channel developers, with our end customers who are looking at a particular project. You know, does it pencil? What is the ideal size? We have this big sort of basket where we put all these inputs about the rate case, about electrical consumption, about location, solar plans, net metering, all these things that come in there. We optimize a design, the size of a project, and we go together with you to actually sell it to the end customer in a manner that maximizes the project economics. When those economics are appealing enough that the end customer will actually, you know, sign up for it and will want to make the project happen, then you come in, you build it, you sell it, and then we get in with the end customer from an operational standpoint. So that's the Power Ops, where we'll really use our dispatch capability, our optimization, which is based in the Google Cloud, where we actually will make those decisions in a centralized manner and then dispatch all the batteries in our network. That's really the heart of our PGM and MISO membership agreement. That's the heart of our dispatch and where we build the value to the end customer. But they need to be able to see it. These are complicated matters. It is complicated to actually see the things in real time. So we've developed two tools for the customers. One is called Power Watch, the other is Power Run. So Power Watch is really the battery equivalent of the solar monitoring, where you see everything that is happening, not only with the solar, but also with the battery in real time. And at the end of the month, you can reconcile all that activity with the financial statements that come from optimizing the solar, optimizing the battery, in the form of a reporting that is updated every day. So it's a dynamic reporting where customers have logging. It's a portal really where they can go in and they can watch their assets and they can have financial dashboards of these systems. Here's a business case I think you wanted to point to. Tim, should I proceed with this, or were you pointing to a question?
Yeah, I just wanted to let our listeners know that they can type questions into the Q&A. So on the toolbar, you'll see at the bottom of your screen, just go to the Q&A and type questions in, and then we'll address those at an appropriate time. But yes, please proceed. This is a beautiful project of Continental's Convergence Energy and Intelligent Generation, the APT project here on the North Shore of Chicago.
Yes, and APT is it's really a destination as much as a retail store. It has a little bit of a Las Vegas shopping mall feel when you get in there. Really beautiful. I'm a hi-fi fan. I love to spend some time there when I go there. But it's a beautiful case of a family-owned company that wanted to do good on top of doing well. And so they have contracted with Continental Convergence several years ago to install solar on the roof and wanted to add the Tesla energy storage systems. I would say that they also had other assets. They had generation assets for their backup, but that were not being used in the most optimal manner. And so when the Tesla battery was installed after the solar, and we were asked to come in and take dispatch, ownership, optimization of those entire assets. So of course the solar produces power whenever it can. There's no really dispatch of solar, but there is dispatch of the generation asset, and there is dispatch of the Tesla battery in a manner that really maximizes the benefit. And here I really want to say this to the industrial customers who are listening in on these calls. We can go into the line items, into the details, into the pro forma economics, but this is really why it makes sense to the APT family. It is a system that allows them to really maximize their renewable energy environmental benefit footprints. It pays back in less than 5 years. We're closer to 3.5 actually. And it is a great showcase for them. So it makes business sense, it makes environmental sense, and they like to show it around. And it is one of the flagship projects that we've done with Continental. We're quite proud of it, and thank you, Continental, for having associated the intelligent generation to it. They like this project, and anyone who would like to see it, we can actually take them on a visit there.
Yeah, and just to give folks a little background, this project was developed by Convergence Energy. They're a solar developer out of southern Wisconsin. We do a lot of work with them here in Illinois. And as you can see, that rooftop, that was a new construction, 100,000 square foot facility. It was very well designed to be solarized. As you can see, nice clean roof. So beautiful, beautiful facility. And you can see the older roof in the background, which has many more roof obstructions than the newer roof. So that's first and foremost, if you're going to build a new facility, make sure your roof is clean so that you can solarize it, because sometimes there are just so many obstructions that it becomes problematic. But I just wanted to answer somebody's, Lewis had a question about demand charges. I don't know that we would get into the customer specific demand charges, Mark, but in general, my understanding is that demand charges are around $7 a megawatt hour in the Midwest, and that could be twice that on the West Coast. Do you have any comments about demand charges, Mark?
Yeah, when we look at it in the Midwest, ComEd here, in this case in ComEd, it's about $7.50 per kilowatt. And it is not enough money to focus all the dispatch of the battery to reduce the demand charges, especially when you have other value streams that would pay you more money in the same moment when you would do demand charge. Now there are some pockets of exception. As you move more towards the east, these demand charges tend to augment. It goes up to $12.50, $15. More towards the eastern side of PJM and even more, but we're nowhere near like the $25 or sometimes even $30 a kilowatt that we've seen in California or Utah or some other places. There are some pockets of exception with some municipal utilities, some islands, if you will. Even inside the ComEd territory here in Illinois, you have places like Naperville, which is a municipal utility in the neighborhood of Chicago. They have demand charges that are in excess of $20 per kilowatt for historical reasons that have very little to do with the actual cost of demand, but that's how the rate case is. So we see some of this in some pockets of exception, but by and large, demand charge is too cheap to be a very, very attractive business case for dispatching batteries in the Midwest. We're able to do it. We have the patents around it. We know how to do it. We just find that there are better things to do with the battery most of the time.
Yeah. Now your slide says double island microgrid. And I know you've explained this to me once before, but what is a double island? And just for any lay people out there, when you have a battery attached to a solar array, if you have the proper hardware, you can create a microgrid so that when the grid goes down, the battery can wake up the solar, and then you're islanding from the grid and just running some key loads, call them critical loads, on the solar and storage, and thereby you can utilize the solar. Normally, the solar array will disconnect from the grid when the grid goes down, and which is a safety feature and a requirement of building codes. So talk about the island microgrid here.
Sure. The request for storage actually originated with the desire to have some kind of protection against the numerous outages from ComEd in that area. And so the Abt family thought that the battery would be a good way to go into autonomous, power sustainability, not sustainability, just power autonomy in moments of outages from ComEd. They already had some generators, but the time it takes for those to come online is too slow for the needs that they had. And so while this system was designed in a manner to pay back, to be joined with a virtual power plant, they really wanted to make sure that it had the ability to provide backup power in case of an outage. And so the notion of microgrid comes into play here, the notion of island. Really, microgrid is a set of behind the meter energy assets that have the ability to operate islanded from the grid. So there's actually a big switch that will disconnect out from the electrical grid when the grid is out, so that it can operate in a completely autonomous mode. So you have then two main assets. One is the generation asset, which is the solar power on the roof, and the other is the battery that allows them to use the buffer in order to have a balancing between the local demand of power in the store and the supply of power from the rooftop. Why double microgrid? It's because they really have two distinct microgrids in the facility. One is the showroom, and the other is all the back office operation. And because of the way this was electrically hooked up, they really decided to have two microgrids. And so the back office operation has one part of the microgrid, and then all the showroom has another microgrid, and they can be independently operated. That has a lot to do with the way the legacy interconnection and electrical connection within the building was done. In the moment of pinch, both microgrids can be rejoined together into one. But it's actually a very nice configuration, and one that has been proven many times over.
So this backup power that the battery allows the facility to have is very important, and it's something that many facility owners want. Some of them truly need it because they're in an area where they have frequent outages. The challenge is that you have to have a battery that is scaled properly to your critical loads, and in this case that was 500 kW. There's also certain ratios that you can pair the size of the battery with the solar array. You can't just install a 10 megawatt battery on a 100 kW solar array and use the ITC. So there are some rules. So you have to connect with us at Continental, or folks like Convergence Energy or Intelligent Generation, who really understand how to size these systems. It's completely non-trivial. You want to say anything else about the APT project, Mark?
Maybe just, let's, two quick things. One on the ITC, I don't want to give the false impression that there are strict rules from the IRS that automatically necessarily allow you to take the investment tax credit on the battery. This is more something that is let's say, based on the sum of private letter rulings and some soft rules that we have developed that allow us to size the battery in proportion to the solar. But at the end of the day, it is the end customer who is making a decision with their tax advisors on how far they can actually take the ITC on the battery. So it is complicated in the sense that there is actually no formal rule from the IRS on this topic, but we can share our experience with customers on that. Yes. The previous slide was really showing what the project looked like. Here is an example of the power run. This is just a screenshot of our dynamic tool called the power run, where the customer can go in this case APT, and go in every day. It is updated every day. Here is looking at the situation at the end of 2019. What is the value stack that has been generated in terms of the sum of the savings plus the sum of the earnings from grid services from all the assets behind the meter? So what is the solar generation, how much solar offset was generated, solar credits, how much was generated, capacity savings, transmission savings. So this is really a prime example of the value stack that we hear a lot about in conferences. Everybody talks about it, but very few people actually do it. And here we have over 2 years of experience doing it, presenting it. These are numbers that are endorsed by APT, and they see those results on their electrical bills and in the checks that we send them at the end of every month for the services they have provided to the grid. This gets updated every day. with the new value. And so this is something that we provide to all of our customers. So yes, that was about finishing apt. We had the description of the business case, and here is how the power run shows the numbers that they can generate.
And Mark, would you just walk through those different slices of the pie and what those, the dark green, light green, blue, red, and yellow?
Sure, and the proportions and the line items might be different for different customers. We are not in a setup or in a system here that is generic. This is what applies to apt, and it might be different for different customers. What we're seeing here in blue in those bar charts is really the amount of money that was generated from providing grid services to PJM. And so this is the amount of money that IG sent to apt from our membership in PJM. So that's the blue value, and it was in excess of $65,000 in 2019. The red is really the value of the solar energy in pure kilowatt hour offset. Now, energy was getting very cheap in 2019. It is now at rock bottom price now in the beginning of 2020. But the kilowatt hour price that apt was paying to ComEd was offset by some of the value of their solar power. And so that represents about $31,000. The value of the solar renewable energy credit was actually more than that because of the previous SREC program that was in place, and that's the one that apt is under. So that was actually a little more than the value of solar offset. That being said, it is a program that will end, right? Once they have generated, I forget if it was 5 or 10 years, Tim, but once those SRECs have been generated, then that yellow will go to zero. Will have helped pay back the system, and it will be the red that will continue for the lifetime of the system. And then we have the two green elements, so capacity and transmission savings, which are line items on the ComEd bill, which we're probably going to go into in a separate part of our conversation.
Great. So if anybody has additional questions about that, please type those into the Q&A. And but this is a great overview of the value stack for a PJM customer in ComEd in Northern Illinois. Just real quick, I'll just recap those. You've got frequency regulation. That is a check that gets written to you from Intelligent Generation. There's the solar energy to grid, right? Solar array is creating energy from sunlight. There's SREC income. 1 megawatt hour of electricity generated by a solar array is 1 SREC. And we have very generous SREC incentives in Illinois today, so contact us to find out more about that. And then you have these other grid services, capacity charge reduction and transmission charge reduction. Mark, could you explain capacity charge reduction?
Yes, let's go there. This is probably going to be the more technical or rule-based part of this discussion. All right. So utility bills are notoriously complicated, and they're built on a lot of history, a lot of explanation, and we do a good job through our power plan tool to actually try and simplify that for a better understanding of its core drivers. And every time we do this in ComEd territory and other places, we see repeatedly that when a customer spends $100,000 or $1 million on their electrical bill in 1 year, it will be very common that they are astounded that less than 50% goes against energy. How much do we consume energy? How much do we consume electricity in a year represents less than 50% of the dollar value of the bill. And so there are other line items. Solar will only offset the energy line item. So how can we attack the other line items when we go into looking at it from a energy storage standpoint? So that requires two things. It requires dimensioning this, and it requires a good understanding of what these things are. Demand power, demand charges, we talked about it a little bit. We, by and large, in Illinois, take it as a given because the value of that is low enough. It can be high on the bill, but the cost of reducing it with the battery is not going to be a good payback. So we want to concentrate the battery use case here on capacity and transmission. Customers will see this as something measured in kilowatt on their bill. And most of the time, they will be confused between demand power, capacity, and transmission. So demand is really like the monthly reset of what was your maximum consumption during a half hour on, in the billable hours, so from basically 8 a.m. to 9 p.m., and it varies by jurisdiction. Capacity and transmission is really something else. It is looking at what was my consumption during those few hours in the whole year when the grid was at maximum stress. Stress for transmission that were congested, or for capacity because there was not enough generating power on the grid. And here's the remarkable thing. In ComEd and in most of PJM, these values that you see here, transmission plus capacity, are about 30% of a customer's bill. 30% of that value is driven by the consumption pattern of the end customer in only 10 hours in the entire year. There is an enormous disproportion between the measurement of their power consumption during only 10 hours and how much they end up paying. This disproportion opens up an opportunity that if we're able to control the usage during those 10 hours, with 10 hours only, we can have an impact and an effect on 30% of the bill. And this is where we absolutely want to focus the use case of capacity and transmission. So how does it work? Well, let me actually go there here, or I could actually share some of our own tools. But here you can see two charts with a lot of ugly line graphs, but this represents the level of stress that exists on the grid, both entire PJM or just ComEd, and the same exists for all the other zones in the PJM territory. The fat line really represents the year in progress. This was 2019. And when it reaches a peak, these are the hours that count for capacity and for transmission measurement. And so you want to make sure, or we, intelligent generation, we want to make sure that we predict very well when those peaks are going to happen. That's number one. And number two, we want to make sure that we're going to put these batteries into maximum discharge mode during those magic 5 hours, we call it internally in the company, during this magic 5 or magic 10 hours, when the discharge of the battery is going to reduce the metered load to an extent that is going to save on the capacity and the transmission charges of the end customer. It gets a little technical, and we're happy to take any prospective customer to the details of these calculations, but it is something that is very both poorly understood and of the highest value in terms of bill reduction. And we have done this successfully together with you, Continental Electric, at APT since we started doing this in 2017. So our hit rate on the accuracy of the prediction is very high. In fact, it's near perfect. And our ability to dispatch also.
Tell us about predicting those peaks. What goes into making that prediction? Because that is the key, right? Is predicting exactly when those hours are going to occur, and then programming the battery to fully charge prior to the event, and then attack the event to the best of its ability and what we're talking about here is, say, a very hot summer day when everybody has their AC running at full capacity. And so the grid is actually humming at its maximum, right? They're producing and delivering as much electricity to the grid in a particular region as possible. So tell us a little bit about how you predict those events.
That's right, and I'll focus the answer on capacity. So indeed, there is a correlation with weather, and in general, at a higher level, the ability to predict a day in the summer, so actually the window goes from the 1st of June to the last day of September, the ability to predict if today or tomorrow is going to be one of those days is not too difficult. You know, I don't want to put sort of too much lipstick on the pig here, but PJM actually presents its own load forecast. If you go to pjm.com right now, you will see a little window in the corner of their website where they actually share a prediction of, you know, how much power is going to be used in the entire PJM territory today, and how the real-time demand is stacking up against the prediction. So the fundamental element, like everybody else who may do that, we also take the prediction from ComEd and from PJM. But then we really fine-tune it with real-time weather forecasts, with updates that are faster adjusting than those issued by PJM, our own experience, and then there is the matter of actually choosing if the peak that you forecast is going to be one of those 5 peaks at the end of the season, right? Because you can be in the beginning of the season and see a peak coming on, you know, the 10th of June, but how are you going to decide if it's a peak when you have the rest of the season to go through, right? So it takes a lot of statistical analysis, backcasting, and modeling tools to actually make a decision on whether you think that not only today, but is the next hour going to be one of those peak hours. And so that's what we do, and we do quite well.
Great, thank you. We have a question about resiliency. And this anonymous listener says, we found that mixing resiliency with other value streams is difficult due to the additional costs to make resiliency work effectively. Can you comment on your experience? And in general, when we talk about resiliency, we're talking about backup power, the ability to operate off-grid for either a short or an extended period of time. And to give the best example that I'm aware of, Mark, is, for example, with injection molding. If an injection molding manufacturer has an uncontrolled grid outage or an uncontrolled shutdown, this can be extremely costly, to the tune of tens of thousands of dollars, because they then have to manually clean out their line with gunked up plastic, and that's expensive for a variety of reasons. So let's talk about resiliency, and when does that pencil?
So I would say it doesn't pencil for everybody, right? Not every industrial user has a need for backup. I just want to preface that. We hear most of the time that they want it, but when we go down into the economics, it's really about identifying the critical needs. So when that critical need is identified, such as in the example that you've just listed, where we're working together on a project with injection molding, then yes, it is the most important thing for the end customer, keeping the production line going and making sure that these bleeps can be avoided so that all the process control equipment doesn't throw up and open up the machines. So there is a cost associated to that. There is a cost of connecting this, because connecting backup power and batteries in a backup power mode so that it will automatically go in requires a different setup than just having something passive that would go offline when the grid goes offline. So there is an engineering and procurement and installation cost that Continental manages very well that will go against this. But then the question was, how do we manage those trade-offs? And in some ways, I will say we don't. Right? It's sort of an easy caveat answer, but let's just say that, for example, we are now in an hour where we're doing frequency regulation for the grid or some kind of grid service. By definition, this service is only provided to the grid as long as we're grid tied, grid connected. If during that hour there is an outage, then it doesn't matter what we want to do, what we choose to do, the system is no longer connected to the grid. So we have to be in default of our frequency regulation obligation for the rest of the hour, and we're going to use a half hour of revenue, for example. But in exchange, we are providing backup to the facility, which is the priority, which is what they needed. So there is, in this case, a natural alignment between the customer prioritization and the economic benefit. Yes, we may lose half an hour, but we're really protecting the facility, and that is what they wanted. So it's most of the trade-offs that we see in the value stack are happening quite naturally. They're not, because they're by and large mutually exclusive. Yes, they're based on their value according to a patented value hierarchy, but it is very rare that we have to make trade-offs that are pulling our hair. They're usually quite obvious.
So the long and short of resiliency is it's totally up to the use case. It's totally up to the individual project owner, how they value resiliency. And it's not easy, but sometimes it is obvious that there is a value, and sometimes it's obvious that there's not a value. So generally speaking, we do find our way through that decision tree, so to speak. We have a couple questions, and we just have about 10 minutes left. So do get your questions in. This is a great opportunity to talk to a true storage expert, and intelligent generation is on the bleeding edge of the virtual power plant concept and practice. So please get your questions in. And then as I mentioned at the beginning, we do post these recordings, so you can find all those at cesnrg.com/podcast. Pooja asks, how will capacity and transmission savings change as there become a higher number of solar and storage adopters in this way? So as solar and storage becomes more common, does the value stack morph?
Oh, that's a very interesting question. If we take electrical bills and at its core, you really have some fixed charges, but you're really paying for energy and you're paying for power. We come from a historical time where the billing was 100% on energy, very little on power, and now we're getting close to 50-50. When we look long-term into the future, all economic systems tend to gravitate to, I would say, really the lowest marginal cost. And as more and more renewable energy comes on the system, the marginal cost of fuel is sunshine and wind. And so that's going to be cheaper and cheaper. So the cost of looking further into 10, 20, 30 years, the balance is going to continue to shift where energy is going to get cheaper and the power related charges are going to become more and more expensive. And so the opportunity for taking control of electricity whenever you need it through tools and distributed generation assets like solar power, like energy storage, is helping end customers and industrial customers prepare themselves to the future, a future where power costs are going to be predominantly driving the cost of the electrical bill as opposed to energy. And so as more and more people do that, the question was really, is there a notion here that oversupply of self-regulating capacity will really lower the market for capacity? I don't think so. And the way the market is actually structured, let's just take a simple example, a very radical example. If we talked about the PJM grid being stressed, and that is what determines maximum capacity. If everybody had the battery and everybody discharged it in that 10th of July 3 p.m. afternoon peak hour on the grid, if everybody was sort of reducing their consumption, then what happens? Then that peak is no longer the peak. Right? Then the peak becomes the hour before or the hour after. So it is a system that sort of self-regulates itself, where the ability to bring your own capacity reduced resources on the grid are going to bring increased benefit into the future, not less.
I guess what is present for me, Mark, is the duck curve. You know, in California on a spring day that's windy and very sunny, they could have 50% grid power now from solar and wind. And as a result, they have the duck curve, right? So they're cranking out renewables in the middle of the day, knocking down the need for other sources of generation. And then as the sun goes down and people fire up their kitchens, the load demands are much greater. And this is a challenge for grid operators. Does storage play an increasing role as we reach 50%, say, penetration of renewables?
Absolutely. The duck curve is a problem because of the utility's inability to accept an excess of distributed generation onto its grid through net metering programs. And there are various solutions and thought processes, around this. But if it comes down to a point where, and we've seen that, where the grid says, I need to put a stop on that. I cannot take as much solar power as you give me. Let me just switch your solar off. And then end customers having this solar generation do not want to waste it. Then they will want to put it in a reservoir, which is an energy storage system. So here we go back into the notion of energy parking. In fact, when you look in Illinois, I'm not saying this is the only solution, but this is just one illustration of how energy storage can be used in the future to sort of mitigate these sorts of issues. I will just point to the fact that in Illinois, in particular, through the FIJA program, there is a smart incentive, smart inverter rebate of $250 per kilowatt of solar inverter for new projects. That is awarded by ComEd and Ameren. Well, everybody takes it, not really thinking what this actually means. This means that those utilities have the power, if you accept that money, in the future. It's not being planned right now. It's being thought about, but not yet planned. But it gives them the legal right to actually have access to your solar inverter and possibly to reduce it or shut it off, some years into the future, if and when the duck curve becomes a problem in Illinois. So there's some good amount of planning that goes into this for the future of the electrical grid in the Midwest.
Then we have a related question from Rob. Are the transmission and capacity price mechanisms the same for California utilities, or are demand charges high enough there to ignore this savings opportunity? So it's basically a question about the value stack in California. Do you have a sense of the relative value of demand charges versus other in California?
Yeah, so the answer to his two questions really are at the highest level, no, they're not the same mechanism. And yes, demand charges can be high enough there to actually justify a battery, but the use case is very specific and it's going to apply to a minority of businesses, not the majority of businesses, especially those that display a load profile with true peaks, not just hills. You cannot think that you're going to have a battery that is fully charged in the morning and that you're going to discharge for 10 hours and then have a minimum reduction of your demand that is going to have a maximum impact on your bill. So the types of I would say load profiles where this really pays maximum value is going to be limited. And then I won't go into this, but the sort of magic 10-hour, magic 5-hour transmission and capacity mechanisms don't exist in the same way in California. They exist predominantly in the PJM territory and also for a good part in the MISO territory, which are the two largest transmission organizations in the US.
Great. And then we have one last question from Aaron. How does intelligent generation monetize the value of frequency regulation?
Great, thank you for asking that question. So we do that through our membership with PJM, for example, or with MISO. So it takes a lot of effort for a software company to actually become recognized as a utility, which is effectively what we are, being in the PJM membership as an active member of MISO. And so that allows us to use after passing technical training and certification and all of that, allows us to use our dispatch software and link it with the PGM system or with the MISO system in order to dispatch the battery when it's not used for these wonderful capacity programs that we were talking about, to actually dispatch a battery in the frequency regulation system of PGM that allows us to be compensated for the service we bring to the grid, and that value is then passed on to the owners of those assets. So that's how it works. You really need to work with somebody like Intelligent Generation who has the deep understanding and the setup and the performance track record of working with the RTOs in this very niche market of frequency regulation, and can pass on the value to you. This is not something that an end customer in their right mind would want to do on their own.
Indeed. Well, thank you so much, Mark. Unfortunately, we're out of time, and I have a feeling that we have whetted the appetite of many people. So now they know just enough to know that there is a tremendous opportunity for solar and storage in Illinois. There were a few things that we didn't get to that, so maybe we can have a follow-on conversation on this platform, especially about the environmental benefits, which, if I recall in the pre-show, we were talking briefly about that, and the environmental benefits are something like triple when you add storage to a solar and storage, or to a solar project. So you can look forward to that on future events. I do want to make a few announcements. On April 28th, we're going to have a case study. Simmons Knife and Saw goes solar, and the owner and president, Colin Murphy, is going to come on and talk about how his executive team made the decision to go solar. They installed a 437 kW rooftop array in the northwest suburbs. And then on May 19th, the Illinois Solar Program Update with Anthony Starr, who is the director of the Illinois Power Agency. So that's a great opportunity for our listeners to do some Q&A with Anthony Starr, which is not something you get to do on a daily basis. So you can look forward to that. Once again, I want to thank my guest, Marc Thrum, Intelligent Generation. You can find him at intelgen.com, or just reach out to me and I can connect you to him. This is Solar Works for Illinois. I'm Tim Montague. Let's grow solar.
Thank you very much, Tim. It's been a pleasure.
Thank you, Mark. Take care.
Bye.